So we left off looking at these bidentate ligands. Um, the first one is ethylene diamine, in which these two nitrogens here attach. Bidentate ligands are called chelating agents. Chelating agents in reference to a claw, like on a crab. And one characteristic property of chelating agents are they're difficult to break off, compared to monodentate ligands. And the reason they're difficult to break off is because if we break one of these bonds, let's say I break this bond here, then this bond's still connected. And so if I break this bond, one, and then try to break this bond, what can happen when I'm trying to break this bond over here is the other bond can reattach. And so if you break one, it flops around, but it flops around such that it can reattach without too much difficulty. And so what we need to do is we need to break these simultaneously. Like if you break both bonds in a coordinated, synchronous manner, then it wouldn't be difficult. But it's hard to break it in sync. And so chelating agents, once they bond, they're difficult to break off. Same thing here. And so anything that forms more than one bond is called a chelating agent. And oxalate would be a chelating agent as well. We have two bonds. This oxalate seems like it should form more than two bonds, though, because when we look at it, I'm only using two of the oxygens. This oxygen here and this oxygen here corresponds to this one with the negative charge and this one. What about the oxygen over here? Can this oxygen bond as well? What would you say? The answer is no. That oxygen can't bond. Why is that? And the reason is because of its shape. When we look at the shape of this oxygen is actually on the opposite side of this thing. And so it wouldn't, and if we flip it over, maybe we could put this sideways, then maybe we could get the two oxygens in the same proximity. If we tried to do that, then we'd end up forming this type of bond. And let me show you here. Rather than doing these two oxygens, which are separated by these two carbons, let's just do these two oxygens here, which is separated by a single carbon. And so if I put the cobalt 3+ here, and then bond one oxygen here and the other oxygen here, like this and this. All right, now this is a funny thing we do with the charges. We ignore the formal charges. So let's say this oxygen were originally negative. It's going to continue to stay negative. We ignore the formal charges as if nothing happened. And then we have a carbon here, and then we have another carbon. This carbon's going to the single bonded oxygen over here with a negative formal charge, and this other oxygen here, which will be double bonded. And yeah, double bonded. Actually, this one should be double bonded too. Sorry, I got this wrong. This one should be double bonded, and one of the lone pairs we're going to use as a bonding pair. So it's going to look something like this. Sorry, I just have to take this as emergency. But go ahead and fill in the rest of that. Go back. So one of the lone pairs on the double bonding oxygen was used to bind here. And so this is what we end up with. There should be a positive formal charge on this oxygen. There should be a 0 formal charge on this one, but we kind of just ignore that and keep everything the same. And so these charges don't make sense when you're looking at it formal charge wise. But none of the charges, formal charges and complexes seem to make sense regardless. And so we just kind of ignore those things. All right. So this appears to be bidentate, and it appears that there are 2 ways that this can happen. One way is we can take these oxygens that are kind of far apart, separated by 2 carbons, or these oxygens which are a bit closer together, separated by one carbon, excuse me. It turns out that the second way is no good. And the reason the second way is no good is because of this. Let's take a look at this carbon on the right here. Can you tell me what the hybridization on this carbon is? On this, excuse me, the oxygen on the right. Can you tell me what the hybridization on this oxygen is on the right? Jessica? Or name? Name? I'm sorry, Abigail? Abigail. And one, okay. Did you guys review hybridization over the weekend? SB3, that's correct. Good. What are the angles in SB3 hybridization? The ideal angle. 109. This is going to be distorted, but we'll just put in the ideal angle here. Now, this is what we call a 4-membered ring. In a 4-membered ring, this carbon, this oxygen is different. This oxygen would be sp2. sp2 angle is 120. But anyway, we could just use this one here. A 4-membered ring has an angle associated with it. What is the angle here? If you have a 4-membered ring, it kind of forms a square. And what are the angles in a square? 90 degrees. And so ideally these angles should be about 109, but in reality the angles are closer to 90 degrees. And what that results in is something called ring strain. The bonds are strained. That is, we aren't getting good orbital overlap in these. So we have this ring strain. And what ring strain results in is instability. And so this instability means this. We come up with a simple rule. The simple rule is 3 and 4-membered rings are unstable. 3 and 4-membered rings are unstable. And so if we tried to bind these two oxygens, it would be unsuccessful. However, a 5-membered ring is fine. Here we have a 5-membered ring. There's no problem. Ring strain is not an issue. Would a 6-membered ring be better than a 5-membered ring in terms of stability? In terms of ring strain? Yeah, actually 6-membered is even better, you know. But 5-membered is perfectly fine. And so what that means is that there are potentially other species out there. Now, oxalate is a anion ligand, and so we changed the ending to oxalato. Ethylene diamine is a neutral ligand, and the name comes from this center part here. This is the ethylene part in the middle. You know, 2 carbons get the eth parent name, eth. And then we have the ethylenes in the center, and then 2 amines on the end. Now, these amines have 1 M to it, and so these are ammonia-like structures. So what if I had something like propylene diamine? So let's try that and see. Propylene diamine. Do you know prop, how many carbons that is? Do you guys know the prefixes? Meth is 1 carbon. Eth is 2 carbons. What's 3 carbons? This is back in chapter 3, you want to review. Meth, F, prop. Prop is 3 carbons. And so propylene diamine is going to have 3 carbons, CH2, CH2, CH2. And then it's going to have these 2 amines on the ends here, NH2 and NH2. So if we have some metal, central metal cation plus X here, and it attacks the central metal here, we form a dative bond here and a dative bond here. How many atom ring is this? Six. So this would be a 6-membered ring, no problem. And so propylene diamine would be expected to be a bidentate ligand. Bidentate. It'd be a chelating agent as well. The one I just wrote, bidentate. Here, let me write that. B-I-D-E-N-T. Actually, let's write it over here. Like Biden with a tate on the end. What's after prop? Prop is for 3 carbons. What's for 4 carbons? Bute is correct. So butylene diamine, any problems with that? No, no problems. And we could go higher, but there are no problems with that. Let's go the opposite direction. So we did ethylene diamine. What would methylene diamine be? So let's try methylene diamine. Methylene spelled M-E-T-H-Y-L-E-N-E. and diamine. This is all one word. 1M or 2M's? Here. One M. So what would it look like? What would methylene diamine look like? It'd have two amines. Now the amines don't have to be NH2. You might, NH2 is common for amines, but it doesn't have to be. It just has to be ammonia-like. So for example, let me show you an amine over here. Amines are the organic, weak organic bases that are similar to ammonia. Ammonia is amine with two M's. This makes an excellent ligand here. We have that. And so this is amine. Ammonia is a ligand. But we have amines that are with one M that are ammonia-like derivatives. So for example, we could have methylamine. I think I showed this one before. Methylamine would have an NH2. And this would be ammonia-like. But we could also have dimethylamine. And so dimethylamine would also be ammonia-like, but it would have a CH3CH2, it would have an NH rather than an NH2. Or we'd have trimethylamine. Trimethylamine would have 3 methyls. And how many hydrogens? Okay, you don't count the hydrogens on the carbon. We're just going to count the hydrogens on the nitrogen. And it has no hydrogens on the nitrogen. And so all these are amines. These are all going to behave as weak ammonia-like bases. And so they're very similar to ammonia. How about this one? We'll throw 3 fluorines on there. And I'm going to call this, let's call this trifluoroamine. Trifluoroamine, is that an amine? Yes or no? What do you think? Well, it's got a lone pair on nitrogen. But is it amine? And the answer is no. This is not an amine. But we probably shouldn't call it trifluoramine. In fact, we probably should name this nitrogen trifluoride. Uh-huh.
Why is it not an amine?
Yeah, why isn't it an amine? To be an amine, we want the lone pair, the nitrogen, to donate the lone pair. So in the first 3, we have a lone pair on nitrogen. But on the 4th one, do we have a lone pair on the nitrogen? Actually, we do. So shouldn't it be an amine? Well, we don't just look at the lone pair. There's one other thing we look for. And so if we want to think in terms of charge, acids tend to be positive or tend to be negative acids, like H+. Positive. Bases tend to be like hydroxide, bases tend to be negative. The reason why this last one is not good is because of this. If we were just looking at the bond polarities, these are all polar molecules. Nitrogen's more electronegative, so nitrogen would get the delta minus here. Nitrogen's more electronegative than hydrogen and carbon. Same thing here. Nitrogen's more electronegative than hydrogen and carbon. This gets the delta minus. Nitrogen is more electronegative than the carbons here. This is going to get the delta minus. So in these first three, we have delta minus on nitrogen, which is good because the more negative it is, the more generous it's going to be with its electron. You know, nitrogen has to donate an electron, and lose it, basically, when we do formal charge count. And so that's good. In other words, nitrogen is electron rich. If we look at the oxidation state, it tells the same story. The formal charge is all 0, but the oxidation states, what are the oxidation states on this nitrogen? Can you tell? -3. The oxidation state on this nitrogen? Same, -3. On this on this nitrogen? Same. They're all -3. In other words, winner takes all. So if nitrogen takes all the bonding electrons and it ends up with 6 bonding electrons and 2 lone pair electrons, which gives it 8 electrons, and the number of valence electrons for nitrogen is 5. And so it normally has 5 valence electrons. If it has 8 valence electrons now, then it's got 3 extra electrons, which gives it a -3 charge. That's how we get that. This one's different. What's more electronegative, nitrogen or fluorine? Fluorine, and that means nitrogen is going to get the positive charge, not the negative charge. So is nitrogen going to be just as willing to donate electrons, negative electrons, if it's positively charged? No. And so it's not going to be as good of an electron donor, electron pair donor. And not only that, let's take a look at its oxidation state. What is the oxidation state of nitrogen here? Well, winner take all. So fluorine's going to take all the bonding electrons, which leaves nitrogen with just 2 lone pair electrons. Nitrogen is supposed to have 5 electrons. It only has 2 electrons. Therefore, it's got a deficit of 3 electrons, which means it's going to be +3 oxidation state. +3 is going to make it a lot less basic. You see? So these ones over here, these 3 are going to be very comparable. However, this 4th one's totally different. Can you see it? And so the 4th one, we don't call it a amine. It's not going to be a very good base at all. And so I'll call it nitrogen trifluoride. Methylene diamine should be good. And so we'll start off with an amine here, and then we're going to attach it to a CH2. And then we're going to attach that to another amine. So methyl's 1 carbon, so we're going to have a 1 carbon chain. So it's just going to be CH2 there. Okay, now what's going to happen if this binds? Here. What is it going to look like? And so we'll put a metal here, metal plus X, and then we'll have the lone pair here form a coordinate covalent or dative bond, and this one will come in. And so the adduct that results here is going to be this. It's going to be metal plus X with a bond here to this amine. Goes to this CH2, goes to this amine, to this. Does that look like a good structure for the adduct? Why not? This is bad. Somebody tell me why. Ring strain, exactly, good. Instead, what's going to happen is this. Just one of these will bind. And the rest of the molecule is just going to flap around. So we'll have a lone pair on this nitrogen. And so it's not bidentate, it's monodentate due to ring strain. All right. Let's take a look at these here. The next one is called EDTA 4-. EDTA is just abbreviation for ethylene diamine tetraacetate. We can use these instead of the formulas. And so EN, that's so we don't have to write this. The formula for ethylene diamine is C2H2468H8N2. Oxalate's not too difficult to write. Oxalate is C2. I ran out of memory. Let me try to close some stuff. That's just attendance. There's no attendance grade, but you do have to attend lab, though, as we talked about earlier. So oxalate C2O42-. So some people, they'd rather just write OX, and it's easier. However, in the name, we have to know how to spell it, because in the name, we write this. In the formula, we could either use C2O42-, or we could use OX 2-. In the name, we have to spell ethylene diamine. In the formula, we could either write the composition C2H8N2 or have the condensed structural formula NH2CH2CH2NH2, or just use EN. EN's neutral, there's no charge. For EDTA, the formula gets more cumbersome, and so most people just use the abbreviation EDTA in the formula. However, when we name it, we have to spell it out, the name. And the name is ethylene. Do you see the ethylene part of EDTA? The ethylene part of EDTA is stuck in the center here. There's 2-carbon chain. It's ethylene. Diamine. Do you see the diamine? Yeah, the diamine are these. This is one amine, except there's no hydrogens bonded. These are just 3 carbons, like trimethylamine. Here's the other amine. So that's our diamine. And then tetraacetate. Tetraacetate, these look like acetate. You know, acetate's when acetic acid becomes deprotonated. And so we have an acetate here, an acetate here, acetate here, acetate here. Like oxalate, we change the ending to oxalato when it's a ligand. And so the same thing here, we're going to change acetate to acetato because it's going to act as a ligand. And so we have the 4 acetates attached here. Now, it looks like there are more than 6 donor atoms. So let's take a look. Actually, I guess I can't erase that. Yeah. And so there's a problem with the oxygen. So for example, did it erase? Maybe it did erase. Yeah, it did. So if I bind this oxygen, which would be preferred, right? Because this oxygen has a negative charge. This oxygen here has a zero charge. So what would make a better base, electron pair donor? A negative or a zero? Negative. This would be better. So we could bind this oxygen, we could bind this oxygen also. But if we bind this oxygen, let's say here on the top left, could we bind this oxygen here on the top? I guess this is left. Can we bind these two oxygens at the same time? Yes or no? No, we can't bind these two oxygens at the same time. Why? If you bind those two oxygens here, the two oxygens I'm talking about, I'll try to bind this oxygen and this oxygen at the same time. What would the problem be? Take a look at your notes from what we just covered and see if you can figure it out based on what we just covered. The one with the double bond wouldn't be as good, as the other one, but it still works, formal charge. That's not the reason it can't form. There's another reason it doesn't. So try to think of another reason. The way I had it drawn earlier, where it maintained the double bond, is wrong. Like here, this is wrong. It doesn't do this. It would eventually go to two single bonds, and one of these, the pi bonding pair, would go here as a lone pair, and so the two oxygens would end up looking identical here. And so that's right. The double bond, yes, but no, because in the end it'd be the same. Was there any other thinking? Ring strain, yeah. So that's it. The answer is ring strain. And so we're not gonna have that ring strain. Instead, these two oxygens here won't be a problem, because if these two oxygens bind, then we would form a 1, 2, 3, 4, 5, 6, 7, 8-membered ring. Is there any problem with the 8-membered ring? No, there's no ring strain at all. And so that's not a problem. But we bind these two oxygens, these two can't. So once we bind these two, these ones won't. However, this nitrogen This nitrogen's far enough away, the amine part combined here. And so the oxygen, this oxygen binds, the nitrogen binds. Is there any ring strain if I bind this second nitrogen? No, because you know what this looks like? Ethylene diamine. Ethylene diamine already binds to. And then we'll bind this one and this one here. And so as far as binding sites go, there's 1, 2, 3, 4, 5, 6. So ethylene diamine tetraacetato is what we call a polydentate ligand. It bites into the central metal in more than one place. And more specifically, this one is known as a hexadentate ligand because 6 atoms can bond to the central metal. So one of the homework problems is to try to draw this. And so I might try to do that here. So I'm going to just pick a central metal. Let's just pick cobalt 3+ here. This. And then cobalt 3+ has a coordination number. Do you recall the coordination number of cobalt 3+ is 6. So I'm going to use wedge dash here to show the octahedral arrangement of 6 bonds here. And so this is what I'll try to do. I'll try to draw this out. So we're going to have one of the oxygens bond here. And then we'll have a carbon. This carbon is going to be double bonded to an oxygen out here. And then we're going to have a CH2 group here. And this acetato group is connected to the ethylene diamine group, which is going to be bonded to the nitrogen here. And so I'll put the amine, the lone pair is going to bond to the cobalt 3 here. Okay, each nitrogen is going to have 2 of these acetate style groups here. And so this is going to come off as a CH2 here. And then a C double bond O. And then an O here. So I have one end of my EDTA here, like this. Okay, then I'm going to bring the other end around. Let me try that here. So I'm going to have my ethylene diamine. Now, do you see that the positions here are adjacent? So if I look at this oxygen and the nitrogen, they're adjacent. So for example, I didn't put the nitrogen here on the opposite end of this oxygen because it's too far away. It won't stretch out that far. And so when I do the ethylene diamine, I'm going to put it in an adjacent position. So ethylene diamine is going to have a CH2 and then a CH2 here and then an N here. Normally it has an NH2, but the N is attached to an acetate group. And so I'll have the acetate group come off here. There's an O. And I'm going to either link it to this one on the right or this one down here. Both of these are adjacent positions. So I'll link this one to the right. Oops. Sorry, I just made a mistake here. Let me correct that. So try this again. So this is going to go to a CH2. Oh no. All right. I drew a little differently than what I was just drawing now, but essentially it's the same structure. We have this nitrogen. Nitrogen has a lone pair. When you look at ethylene diamine tetraacetate, it's going to have two acetates attached to it. So these two acetates are coming off on the right. There's one coming towards us, and there's one going behind. This blue line here. And then we have the oxygen binding here. And let me fill in the lone pairs here. All right, so those are our two acetates coming here. Then the lone pair is used here, and then we have the ethylene diamine. The ethylene diamine is binding here, these two spots. And then this nitrogen on the amine has two acetates that are coming off, that are binding here. And this is supposed to be octahedral. So I was going to try to draw more octahedral-like in this case, but it didn't come out quite that good, the drawing. Let's take a look at some structures for this here. This would be ethylene diamine tetraacetate. So the green's cobalt in the middle. The reds are oxygen. The blues are nitrogen. So if I look at the blues here, they're going in the back, and then there's an ethylene chain behind connecting those. And these reds are attached to these acetates. And so this gives us a coordination number of 6, and it's a hexadentate ligand. There's only one ligand with a coordination number of 6. And so that was our attempt to draw it. This ligand is extremely difficult to break off. Extremely, you'd have to break all 6 bonds. And the problem is it reattaches quite quickly. And so if you break one bond, then go on to the next, and eventually these things reattach. Yeah. And so this is an excellent chelating agent. One of the things here is keep in mind that the lone pairs of electrons of polydentate ligand must be far enough apart to attach. What's this keep in mind about? This keep in mind is about ring strain. This is from the book. They have to be far enough apart to avoid ring strain. And then there's one more keep in mind from the book. Let's see if I can find that. Here. Keep in mind that the EDTA4- ligand is not planar, as suggested in table 24.3. Use Vesper. I told you Vesper doesn't work. Vesper doesn't work for the complexes and the bonding in the complexes itself, but within the ligand, then you expect it to work. And so use Vesper theory to gain an insight into the shape of this polyatomic anion. And the shape of those polyatomic anion is it can flop around. When we have single bonds, there's free rotation. So when we look at this would be an sp3 nitrogen, sp3, 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 a lot of sp3 bonds in there. So it's going to give it a shape. And the shape we can get a better idea by looking at something like this. A lot of tetrahedral angles. Do you see that? There are 109 angles. Would be the ideal. Okay. So that was the other keep in mind section. Sometimes we try to draw these three-dimensionally. Oxalate is planar. This is all sp2. This is flat pancake. This is kinked because this is sp3. So we expect it to be kinked. And so Vesper works for ligands like this, but it's not going to work when we look at the bonds to the metal. All right, now cobalt has a coordination number of 6, but I only have a coordination number of 2 here, in a bent configuration. And so I could actually attach more ligands. So here, this is one ligand, one gigantic ligand that completely encapsulates that cobalt-3. But there are other structures here. So for example, if I have 6 positions here, I have other options. Rather than putting one hexadentate, I could put 3 bidentates. So for example, if I do ethylene diamine, now I did the formula, but I can use the abbreviation instead of the formula here. So En. So this is the abbreviation for ethylene diamine. 2 nitrogens bonded, and I'll just write En there. They have to go into adjacent bonds. I can't go opposite 180 because it's too far away. And so if I put one nitrogen here, I can't put the other nitrogen on the opposite end. I have to put it either here or here. Let me put it here. And so this would be another ethylene diamine. And this would be another ethylene diamine up here. And so in this case, I built this complex with 3 ethylene diamines, which gives it a coordination number of 6. This is 1 EDTA with a coordination number of 6 as well. And so I can fit in, or I can fit in like 2 bidentates and 2 monodentates, or 1 bidentate and 4 monodentates. There's different variations we can have of that. And so those are the ligands there. Yeah.
Sorry, what does that say from connecting the nitrogen to nitrogen?
En. En's abbreviation for ethylene diamine. I could do the exact same thing with, What do you name this? All right. The name for this is, it's called tris, not tri. It's called tris parentheses ethylene diamine. Now we can't use the abbreviation in the name, so we have to learn how to spell it. And so it's ethylene, E-T-H-Y-L-E-N-E, diamine, D-I-A, with 2 M's or 1 M? 1 M. Okay, the reason we have to use tris is because di is part of the name of the ligand. And so we don't want triethylene diamine. That would mean 3 ethylenes and 2 amines. And so this is trisethylene diamine, and then the central metal, cobalt 3. There's a charge on cobalt 3. Let's see, my pen is a little bit bad. The formula for this is kind of opposite. The formula for this is we write the central metal first. And so let me go ahead and write the formula for this. And when we name it, we name the ligands first. When we write the formula, we put it in square brackets. That's to indicate it's a complex. And so we write the central metal first. And then here we can use the abbreviation if we want, or we can write the complete formula. And so we will just write this cobalt En sub 3, 3 plus. This is the cation. That would be it. The name of this one is a bit different, though. Okay, we can't use the abbreviation for the ligand, so we have to spell it out. So ethylene diamine is the same. Ethylene diamine with 1 M. Tetraacetato. This is all one word. Tetraacetato. Now this is one complete unit. So it's not one ethylene diamine. We might get confused because there's ethylene diamines as well, right? And so we're going to put it all in the parentheses so that we don't think this is one ethylene diamine and 4 acetates. This is ethylene diamine tetraacetato. Cobalt. Now, the funny thing happens here. What's the charge on ethylene diamine tetraacetato? 4 minus. What's the charge on cobalt? 3 plus. And so the net charge comes out funny because over here we had a positive charge. Over here we throw the cobalt in the center. It's still cobalt 3. And then here we could use the abbreviation. For ethylene diamine tetraacetato, there's no problem using the abbreviation because there's so many atoms in this. And so we have a 4 minus and a 3 plus, which gives us a net charge of what? The whole complex is going to be negative. Now, this is called a complex anion. This is called a complex cation. Now, for complex anions, we do something funny with the name of the metal. And so we have cobalt, but what we're going to do is we're going to change the name or add an 8 to it. The 8 is to indicate that it's negatively charged complex. It's an anion complex. So whenever you see an 8 on the metal, that means we have an anion complex. If there's no 8, like over here, that means we have a cation or neutral complex. And so if I see cobaltate, then I know we're dealing with an anion complex, and it's going to be cobaltate. And the cobalt is actually +3. And so when I say an anion, it comes from adding up all the charges. And so this is called ethylene diamine tetraacetate cobaltate 3. We do something even funnier. Did I talk about Latin names for elements? No? Okay. So let me go back up to the rules here for nomenclature, or go back down to the rules for nomenclature. So there are two numbering systems. Have I talked about this yet? No. Okay. This is from the morning, so I have it all marked out. I'm just using the morning notes since I lost the afternoon. All right. Whenever we have an anion ligand, I talked about this, correct? Anion ligands, we change the ending to O. Did I talk about this? Yeah. Neutral ligands, we just use a normal name, like ethylene diamine. It's ethylene diamine. Unless it's 4, one of these 4. Water is called what? Do you have this in your notes? Aqua. And so we have to use aqua instead of water. Ammonia is called amine. Amine with 2 M's or 1 M? 2 M's. When you see amine with 2 M's, it means ammonia as a ligand. Carbon monoxide is not carbon monoxide, it's called carbonyl. And nitrogen monoxide used to be called nitrosyl. And so nitrosyl was easy to remember because if you knew carbonyl, then nitrosyl seemed pretty logical. Except they don't call it nitrosyl anymore. Do you know what it's called? It has a kind of a cumbersome name. Oxidonitrogen. I don't really like this name at all. I'd much rather call it nitrosyl than oxidonitrogen. If the ligand has a prefix in the name, like ethylene diamine or ethylene diamine tetraacetate, then we have to go to the next numbering system, which is bis for 2, tris for 3, tetrakis for 4. So we have 2 numbering systems. We always use numbering system number 1 unless the name contains one of these, then we'll switch to numbering system number 2. So an example, bis ethylene diamine means we have 2 ethylene diamines. What if we had 2 oxalatos? If we had 2 oxalatos, what would we use di or would we use bis? If we have two oxalatos, should we use di or bis? Now we look at the name for oxalato. Oxalato, does it contain a prefix in there, in the name itself? No, so we just use di. There's not going to be any confusion. And so the only time we go to the secondary system is if the primary system is already in use. When we name a complex, ligands are named first. So it's kind of weird. It says backwards. So all this stuff is just this. When we name, the ligands come first. When we write the formula, the metal comes first. So it's opposite. So let's take a look at the two names we just did. When we name, the metal comes last. When we write the formula, the metal comes first. Here, the name, metal comes last, ligands first. Formula, metal comes first. So it's opposite. So just remember that. In names and formulas of coordination compounds, cations come first, and then anions. It's like sodium chloride. Cations always come first. Before 2005, there was a rule that anion ligands come first, followed by neutral ligands. And so before 2005, it's not all alphabetical. After 2005, it's strictly alphabetical. And it's going to be alphabetical based on the name, not alphabetical based on the formula. If we do alphabetical based on the formula, then it gets difficult because if you have something like ethylene, diamine, tetraacetato, which element do you pick? You know, carbon, hydrogen, oxygen, nitrogen, which one? And so we don't do that, at least not anymore. So let's take a look at some examples here. Oh, I didn't want to delete everything. All right. So first we're going to go from the formula to the name. Now, in the formula, the essential metal comes first. In the name, the ligands come first. We can tell what the complex is. The complex is within the square brackets. And so in this case, we have a complex cation. And the anion is just normal. This is just chloride. It's not chlorido, just plain old chloride. So this would be like sodium chloride, except we don't have a sodium ion, we have a complex cation. So let's name the complex cation first. So if the metal is coming first, then we want the metal to come last. And so we do the opposite. So when I look at the formula, the metal's coming first, therefore the ligands come first here. And so what's the name of the ligand here? Ammonia is not called ammonia, it's called amine with 1M or 2M? With 1M. Do we use the primary system, di, or the secondary system, bis? The primary system. So this is going to be called diamine with 2M's. Okay, so now the ligands come first, so it's the opposite of what we see, followed by the metal. The metal name is silver, diamine silver. Now, silver only has one charge. What is the charge on silver? Silver is always plus, not plus 3, plus 1. Silver is fixed charge. It's always plus 1. And so if you had a silver chloride, AgCl, do you call that silver 1 chloride or just silver chloride? Just silver chloride. Why? Because silver is always 1. So we don't need it. It's a waste of space. However, in complexes, we always put the charge as the metal, even if it's only one charge here. And I think the reason for that is because sometimes these ligands can capture neutral atoms. So neutral atoms can be attacked as well. So it could be silver 0 with no charge. In this case, it's silver 1. How do I know? How I know is because ammonias are neutral, chloride is -1, and so this whole thing has to be +1. And so we're going to have diamine, silver 1, chloride.
So you want them to walk like the square brackets first.
Yeah. We name the cation first.
Okay.
If the square brackets come last, we'll do the cations first. So in E, the square brackets come in last, so we'll do the cation first, which is this rubidium there. Okay, this is a complex cation. This is normal anion. What's this anion called? SO4 is called sulfate. What's the charge on sulfate? 2-. So this whole complex must be 2+. To balance out the charge. So if we have a 2-, we need a 2+ to balance the charge. So what is the charge on copper here? Yeah, water's neutral, ammonia's neutral, so that's got to be a copper 2. But copper 2 we don't write first, because if we see the metal first here, then the metal must come last in the name of the cation. So now we go on to water, which is called aqua, and ammonia, which is called amine. So which one should we name first, the amine or the aqua? The amine. And so we're going to do it alphabetical. We ignore the prefix. So this is going to be called tetra for 4. Tetraamine. Now amine is with 1 M or 2 M's? 2 M's. Tetraamine. Okay, how many aquas do we have? 2. And so we're going to call it tetraamine diaqua. We're still in the primary numbering system. There. Tetraamine diaqua. And the name of the metal? Copper. Now copper is variable charge, so this copper is going to be copper 1 or copper 2? 2. So the whole name of this is all one word, tetraamine diaqua copper 2. There are no spaces. And then we're going to have a space between that cation name and sulfate. So it's tetraamine diaqua copper 2 sulfate. Coordination number of copper is what in this complex here? What is the coordination number? Is this sulfate bonded to the copper? Maybe the sulfate, that looks like a bidentate ligand. Would sulfate be a bidentate ligand? No. Sulfate is a monodentate ligand, ring strain. In fact, is sulfate even a ligand? Sulfate is not a ligand. Sulfate is just a regular ion. So we don't call it sulfato or sulfato, we just call it sulfate. What are the ligands? The ligands here are the aqua and the amines. So what's the coordination number of this? So aquas are monodentate, amines are monodentate. Altogether we have 6 total. Do you see that? And so that's 6. So is the coordination number 6? Or should I add the sulfate? Sulfate should be monodentate, so that's 7. Is the coordination number 7 or 6? It's 6. Only the things within the brackets are bonded. The stuff that's outside the brackets is ionically bonded. The stuff inside will be covalently bonded. And so the coordination number is 6. Well, that's a common coordination number for copper. In fact, did you guys look at the coordination numbers? We're not going to have to predict anything because do you see a pattern with the coordination numbers? We looked at the coordination numbers before, didn't we? Or did we? So copper 1 has coordination number 2 and 4, but this is copper 2. Copper 2 has a coordination number 4 and 6. So in this complex, it's got a coordination number 6. In the previous example, we looked at silver. Silver only has one coordination number, 2. The silver ions, Ag+. Those form linear structures here. And that's what we see here. In the diamine, this would be coordination number 2. Do you see that?
Does amine go before aqua because it's alphabetical order?
I'm sorry?
Does amine go before aqua because it's alphabetical
Yes.
order?
If it's alphabetical order according to the name, not the formula. If we did it based on the formula, then aqua should go first. H. You know. Or is the coordination number of silver 3? What is the coordination number of silver in A? 2 or 3? 2. 2 is correct. It's within whatever's inside the brackets. Outside the bracket, it's ionically bonded. So we don't consider that directly bonded to the silver. Here, they forgot the brackets here. So let's put in the brackets here. This is neutral, so the charge is actually 0. If the charge is 0, ethylene diamine, is that neutral or does that have a charge? Ethylene diamine is neutral. There's no charge. How about chlorido? Is chlorido neutral or does it have a charge? It has a charge. What's the charge on chlorido? Minus is correct. And we have 2 of them, so that's minus 2. Therefore, the charge on platinum is plus 2. All right, what's the coordination number here? Is the coordination number 3? I have 3 ligands attached to it. So is the coordination number 3? No. Coordination number is not 3. What is the coordination number? It's not 2. It's not 3. It's not 2. It's not 1. It's not 5. It's 4. Coordination number is 4. How come? A chloro is monodentate, but ethylene diamine is bidentate. And so it's going to actually bond in 4 places. So that's platinum 2. Platinum 2 typically has a coordination number of 4. And so when we look at platinum 2, it has a coordination number of 4. Now, if it has a coordination number 4, it could either be square planar or tetrahedral. And we don't use Vesper here. Do you know what it is? It's square planar. And so these are just the observations. So you try to make sense of these observations by trying to find some kind of pattern to it. You may or may not. So we have this. Now, how would we name it? So here, look, the metal comes first here. So that means the metal is going to come last there. And so we got to do it. Chlorido or ethylene diamine, which one should come first? Chlorido, because of the C. C comes before E. So this is going to be dichlorido.
Would it be wrong if you put it that way?
Not necessarily. No.
For test-wise?
Yeah, test-wise, it would be wrong. Dichlorido. Then, can I use the abbreviation, or do I have to spell out ethylene diamine?
Spell it.
I have to spell it out, unfortunately. Ethylene diamine with 1M. Platinum or platinate? Platinum. When would I use platinate? I'd use it if this whole thing carried a negative charge. So if it's neutral or positive, then we don't change the name of the metal. And the oxidation state of platinum is +2, so I'll write Roman numeral 2. So this is not an ion. This is just the dichlorido ethylene diamine platinum 2 molecule. Now ethylene diamine is all one ligand, so we might try to insert parentheses here to keep it together, like that. Uh-huh.
So that one there you think it as a forward, correct?
Yeah.
So then why above would it be sulfate when there's no charge carried to that molecule?
Because on the left here is the cation, which is the tetramine dialkyl copper 2. The tetramine dialkyl copper 2 is actually +2. And so we're naming this like calcium sulfate. This would be like calcium sulfate, but we don't have calcium. We have tetramine dialkyl copper 2, which is +2, just like calcium. And so we name it like an ionic compound.
It's distinct because it's bonded ionically rather than the platinum there is bonded more intrinsically.
Yeah, okay. Within the brackets here,
Okay.
that would be it. And since it's neutral, we don't need an anion to balance charge. So that's why there's no anion there. All right, let's take a look at D. So the metal comes first here. That means the metal is going to come last there. And so we'll do the ligands first. Aqua versus bromido. Which one should go first? Aqua. And penta is for 5. So it's going to be penta aqua. Penta aqua bromido. Chromium or chromate? It's going to be chromium because even though we have a negative anion, bromide or bromido, the whole complex is positive. And so this is going to be chromium. What's the charge on chromium? 2+. So it's going to be Roman numeral 2. Well, is that correct? Because if chromium is +2 and bromine is -1, +2 minus 1 adds up to what? +1, but this whole complex is +2. Waters are neutral, so it cannot be chromium 2. It has to be chromium 3. That means if I have +3 minus 1, that gives us +2. Waters are 0. Does that make sense? All right, why don't you try to do number or letter E here. This is an ionic compound as well. This just has a normal cation. What's the name of this cation? It's a group 1. It's called rubidium. What's the charge on rubidium? +1. That means this must have a total charge of -1. And so let's name this. Now, when we name the complex, we do the opposite of the formula. So in the formula, the metal comes first. In the name, what's going to come first? The ligands. And so what do we name F? Fluorido. And we have how many? Tetra. So this is going to be tetra. Now, there's going to be a space between the cation name and the anion name. So it's rubidium, tetra. Should I call it monorubidium or just rubidium? Just rubidium. And tetrafluorido. Fluoride is FLU or FLO? FLU. Tetrafluorido. Okay, now this whole complex has to carry a charge of -1 because a rubidium is a +1, correct? And if it's a negatively charged complex, then what do we do with the name of the metal? We use the 8 ending. Okay, so if I have an anion complex, I have to use the 8 ending. So this should be silverate. Silverate. But we do something special for these elements. We use the Latin name for these. The symbol is based on the Latin name. So iron has a weird symbol, it's Fe. That's because it's ferrium. And so rather than calling it ironate, we call it ferrate. Copper symbol is weird because it's cuprium. And so rather than calling it copperate, we call it cuprate. Tin is Sn or stanium. So rather than tinate, we call it stanate. Silver is Ag, argonium, something like that. And we call it, rather than calling it silverate, we call it argentate. Lead, plumbium, is called plumbate, not leadate. Gold is called orate, not goldate. So these elements, the ones with these Latin symbols, are going to have the Latin name. Okay, sodium isn't that common in anion complexes, but if there's sodium in an anion complex, we might call it, rather than sodiumate, we might call it nitrate, from natrium, something like that. And so here, rather than calling this silverate, I'm going to call it argentate. And so this is all one word, argentate. What must be the charge on silver here? If silver is +1 and then fluoridos are -1, do the charges add up? No. That means the charge on silver must be +3. This has got to be argentate Roman numeral 3, otherwise the charges don't add up. And so if silver is +3 and fluoride's -1, and I have 4 of those, so +3 minus 4 gives me -1. And that balances out the rubidium. But there's a couple of things to note. One, the complex is all one word. So tetrafluorido, argentate, 3 is all one word, so there are no spaces. But we have a space between the cation and the anion. One weird thing is this. In Chem 1A, you learn that silver's fixed charge, and silver's charge is +1. Do you ever recall seeing silver in +3? No. And there's one other thing that's weird. When we look at the coordination numbers, what's the coordination number of silver? Is the coordination number of silver 2 and 4, or just 2? If I look at silver here, the coordination number is just 2, and it forms linear. And so how reliable is that data? That data actually is pretty reliable here, and it turns out that this has got to be a typo. This must be a typo, is my thinking. My thinking is this is not a 4. That should be a what instead? It should be a 2. And that's going to make it a di rather than a tri. And that's going to make the charge 1 instead of 2. And so I think this is a mistake. This has got to be rubidium AgF2. If it's AgF2, then that's good because the coordination number of AgF2 would be 2. And the charge, what would the charge on silver be? +1. And so I'm thinking that this is a typo, and it should be rubidium difluorido argentate 1. Now it makes sense. And so this isn't right here. Okay, let's go on to F. F, should I call that disodium or sodium? Or natrium or nitrite or nitrate? What should I use? Sodium. It's just a normal sodium cation. But we have a complex anion. So again, we have a complex anion. In a complex, the metal goes last in the name. And so we have to name the ligands first. So cyanido, or what's NO called? Nitrosyl, or the new name would be oxidonitrogen. And I don't particularly like oxidonitrogen, but let's use it. Oxidonitrogen or cyanide, which one would come first? Cyanide. So it's going to be sodium space penta cyanido, pentacyanido, and then this one, this weird one, is oxidonitrogen. Iron, ironate, or ferrate? It's going to be ferrate because the whole thing's got to carry a net -2 charge. I have 2 positive sodiums. And so this is going to be ferrate. And then what's the charge on iron? 2. All right, cyanide is -1, so that's -5. Oxidonitrogen is neutral. It's just nitrogen monoxide. And that means iron has to be +3. So this is going to be ferrate 3. And that way we get +3 from the iron, -5 from the cyanide gives us -2. The -2 will balance out the 2 positive charges. Does that make sense? All right. Now the oxidonitrogen, I'm going to put in parentheses here because oxido is a ligand and nitrogen is a ligand. You know, nitrogen can act as a ligand as well. It's not on our chart there, but let's see nitrogen acting as a ligand here. Nitrogen can act as a ligand because it has lone pairs that can donate. Is it going to be bidentate or monodentate? Nitrogen. Bidentate? Okay. Monodentate? Monodentate is correct. It's not bidentate. And so this can act as a monodentate ligand. In fact, nitrogen can, oxygen can also act as a monodentate ligand. This would be oxygen here. And so it's not a great ligand. And so we have iron 2+ in hemoglobin. And what happens in hemoglobin is the oxygen binds to the iron 2+. It forms a coordinate covalent bond. Now, the coordinate covalent bonds aren't all equal in strength. This one happens to be fairly weak. When you have a strong bond, it forms a pretty inert, unreactive complex. When you have weak bonds, it forms a pretty weak reactive complex. And so oxygen would be on the weaker, more reactive side of things. We give a name for that. We call it labile. If the ligand is labile, it's easy to break off. Very easy to break off, which is good because hemoglobin acts as a transport mechanism for oxygen. If the oxygen doesn't break off hemoglobin, then you aren't going to be able to use it. This is hemoglobin here. Can you tell what the coordination? This is iron 2, the brown atom in the center. Can you tell what the coordination number of iron 2 and hemoglobin is? 6. 5 of these are from the hemoglobin, and the 6th one is from this ligand here. Can you tell what this ligand is? It's CO. What is CO? CO is carbonyl. So this is a carbonyl bonding to this. What's another name for carbonyl? Carbon monoxide. And carbon monoxide is an excellent ligand. In fact, if there's a competition between O2 and carbon monoxide, do you know who would win? Carbon monoxide is clearly the winner. One of the reasons is take a look at the formal charges. Can you tell me what the formal charge on carbon is? You guys have a chance to review the formal charge? Okay. One way we count the formal charge is we split all the bonds 50-50. So if you split all the bonds 50-50, then that leaves, out of the 6 bonding electrons, 3 go to carbon, 3 go to oxygen. So if carbon gets the 3 bonding electrons from splitting those, and it has 2 electrons here, that's 3 plus 2 gives us 5 electrons. How many electrons does carbon normally have? 4. So that gives it an extra electron. An extra electron means it has an extra negative charge. How about oxygen over here? Well, we split the 6 bonding electrons. 3 goes to the carbon, the other 3 go to oxygen. So that's 3 plus 2, that's 5. How many valence electrons does oxygen normally have? 6. So it's lacking 1 electron, so it's got a positive charge here. Which is a better donor? A positive oxygen or negative carbon? Which one would be a better electron pair donor? Which one's going to attack iron 2? The carbon or the oxygen? The carbon, for sure, right? So if there's a fight between this carbon and this oxygen, who would win? Let's say there's a fight between this oxygen and this carbon, which one would win? The carbon. And in fact, the carbon binds so strongly, it forms an inert complex. Inert complex means once carbon monoxide is bonded to the iron 2, once carbonyl binds to the iron 2, it doesn't let go. If it doesn't let go, can oxygen come in? No. And so this is carbon monoxide poisoning, and lots of people die every year from carbon monoxide poisoning because it blocks O2 out. And you can't breathe. Well, you can breathe, but you're not getting any oxygen. And so I guess you can't breathe. All right, let's go the opposite direction. We're going to go from the name to the formula. Squeeze that down. So we see an ionic compound here. Potassium, is this our normal potassium ion? This is just K plus. Space anion. The anion is a complex anion. So let's see what this is. It's hexacyanidoferrate 3. So what comes first, the ligands or the metal? Well, if the metal came last here, then it'll come first here. So what is ferrate? What metal is that? Ferrium, which is what metal? Fe, which is iron. Yeah. So we'll write the iron first. And then hexacyanido. Hexacyanido is 6 what? CNs, 6 cyanides. And then what's the total charge on this? Cyanide is -1. We have 6 of those, so it's -6. Iron, they're telling us, is +3. So -6 plus 3 gives us a -3 charge. So this will be a 3 minus ion. Potassium is +1, so we have to add these up so charges are balanced. So we'll need 3 potassiums for every hexacyanidoferrate 3. It's ferrate because the complex is negative. But the compound is neutral here. So that would be it. Normally these are solids. This would be water soluble here. All right. We'll go on to the next one. Bis-ethylene diamine copper 2 ion. So this is not cuprate. If this were cuprate, it would be an anion. Since it's a copper 2 ion, it's got to be a cation. So let's go ahead and write the formula for this. What comes first, the metal or the ligands in the formula? So the metal came last in the name, therefore it's going to come first in the formula. So copper is just Cu. Okay, then we'll do the ligands. So what is the ligand name? Ethylene diamine. What is the ligand formula? En. So you're allowed to use the abbreviation here in the formula, not in the name. And how many ENs do we have? Bis means 2. All right. En, does it have a charge or is it neutral? Neutral. And so this whole thing is going to have what charge? 2 plus. So this is the bis-ethylene diamine copper 2 ion. What is the coordination number of copper? Is the coordination number 2? It's not 2. It's 4. The coordination number is 4. Why? The reason is because ethylene diamine is a bidentate ligand. So coordination number is 4. All right, why don't you try C and D and E? Try those and see what you get. I'll be right back. Somebody get the formula for C? Anyone?
Al.
Okay, Al. H2O5. OH. Bracket. Chloride 2. Like this? Okay. Yeah, so you wrote the aqua before hydroxido. That makes sense, alphabetical, according to name. and then aluminum first. And that would be the correct charge. Hydroxido is -1, aluminum's +3, so that gives us +2. So that looks good. How about D? Did somebody get D? D is tricky because this is going to be both. Actually, no, it's not tricky. This is just a normal anion here. So it's a complex cation, just like C. So if it's a complex cation, we'll square bracket. And then if the metal came last, the metal's got to come first. So it's chromium. And then which should I write? Amine, chlorido, or ethylene diamine? Well, it's alphabetical, so we're just going to go alphabetical here. So we're going to go amine, NH3, chlorido, Cl, and bisethylene diamine means what? 2 ENs. Okay, what's the charge on this going to be? So chromium is +3, ammonia is 0, chloride is -1, so +3 -1 is +2. Ethylene diamine is neutral, 0. So this whole thing is going to be +2. And then we have a sulfate. We only need one sulfate to balance out the charge. So a sulfate would be -2. And so this would be the formula for that. What's the coordination number of chromium in this complex? Six is correct. Ammonia is monodentate, chlorido is monodentate, but ethylene diamine is bidentate, and we have 2 of those. So we're going to get 4 from that, and then 2 more, 6. E is an example of a complex cation and a complex anion. The complex cation has iron as the metal. The complex anion has ferrate as the metal. In other words, both of these complexes have the same metal. Okay, it's just one is called iron, the other is called ferrate because the cation has an unmodified name and the anion has a modified name. So let's go ahead and build the cation first. It's a complex, so we're going to do square bracket. And then iron comes first, which is Fe, followed by the ligands. And in this case, I have tris ethylene diamine, which means how many ethylene diamines? 3. What's the coordination number of iron in this complex? It's also 6. Each ethylene diamine is bidentate, so it's 2 times 3 is 6. What's the charge on this complex? The charge is +3. Ethylene diamines are neutral. So I'll just write it here. This is a 3+ cation because I don't know how to balance these just yet. And so we have a complex anion. What goes first? The metal comes first. If the metal came last here, the metal comes first here. And so we're going to have Fe, and then it's hexacyanido, which means we have 6 cyanides. What's the charge on this complex here? Minus what? 4? Yeah, that's correct. -4 or 4 minus. It's +2 minus 6 gives us -4. And so the easiest way is just to cross multiply. And so I'm going to need 4 of the first complex and 3 of the second complex to balance the charge. The common factor will be 12. And so 4 of these and 3 of these. Give me +12 and -12 cumulative charge. And so this would be the trisethylene diamine iron 3, hexacyanidoferrate 2. That would be a compound. So those are some examples of nomenclature. And so we're going to leave this now, and then we're going to use the remaining part of lab to look at chemical reactions. Good? Okay. For the chemical reactions, we're going to look at the chemical reactions homework. And so let me pull that up.
Is there still manual?
No, there's no lab manual.
There's not manual.
Yeah. There's not going to be one. Let me see. Okay. So reaction 1 we already did. So let's take a look at reaction 2. Reaction 2 we did something very similar to that. And so I'm going to go through a few of these here. Let's go through reaction 2, 3, 4, and 5. Yeah. All right. Reaction number 2 is solid potassium sulfide. What's the formula for potassium sulfide? Has anybody already done this? Reaction 2? The homeworks are due on the exam dates. Normally what I look for on the homework is just if you attempted all the problems. That's it. So potassium is K plus, sulfide's S2 minus, so we'll need 2 potassiums for every sulfide, and this is solid. In sodium chloride solution, the sodium chloride will be aqueous. So I'll leave it blank or write AQ. I'll just leave it blank. And so what should form here? If you look at this reaction just looks like an AB plus CD. If it's an AB plus CD reaction, then we're going to get potassium chloride and sodium sulfide. Right? In other words, double replacement. Usually when I'm trying to figure out if a reaction occurs, I'll always go double replacement first, because double replacement is normally the easiest. And so if it's this pattern, I'm going to go double replacement here. And then I'll look for a driving force. AB plus CD yields AD plus BC, or CB, excuse me. So is there a driving force? Potassium salts are all soluble, so that's aqueous. Sodium salts are all soluble, so no precipitate. How about gas? Is potassium chloride a gas? Sodium sulfide a gas? No gas. How about stronger acid to weaker acid? Are we going from a stronger acid to weaker acid? No. No stronger acid to weaker acid. And therefore, NR. NR stands for no reaction, but I have to be careful here. I should say that there's no double replacement reaction. There could be other reactions. So this was not going to react to form those. And so the next thing I would do would be acid base, Bronsted acid base. That would be the next. And so what should we do about potassium sulfide? Is potassium sulfide, well, we're taking solid potassium sulfide and putting it into a solution of sodium chloride. The solution of sodium chloride consists mostly of water. So if we take our potassium sulfide and dissolve it in water, will it dissolve? Is potassium sulfide soluble or insoluble? It's soluble, group 1 salt. So if I have potassium sulfide solid and there's water present from the solution, then I look at solubility first. And solubility says potassium salts are soluble. It's going to just go K2S, aqueous. To emphasize aqueous, I'll write AQ here. When I have potassium sulfide aqueous, the next thing I look at are electrolyte properties. Should I split it up, i.e. ionize it, or just leave it alone? Well, I ionize the strong electrolytes. The strong electrolytes are the strong acid. Potassium sulfide, is that a strong acid? Strong base or soluble salt? Well, for sure it's a soluble salt. All potassium salts are soluble. So it's a soluble salt, so we're going to break it up. And so it's going to go into 2 potassium ions plus the sulfide. $2K plus. 2K plus the sulfide, S2 minus. Now, what you should recognize is sulfide is a strong base. So immediately I see a strong base, but do I see any acids? No. However, there is an acid present. What's the acid that's present? Water. And so let's take a look at the strong bases. A lot of you have already memorized the 7 common strong acids, but have you memorized the strong bases? No. So what are the strong bases? Probably the most common strong base is OH minus or NaOH, sodium hydroxide, let's say. KOH, another one. How about MgOH2? MgOH2 has twice as much hydroxide, so it should be twice as basic. Is that correct? No. Sodium hydroxide is strong, but MgOH2 is not a strong base. It's a weak base. So not all hydroxides are strong. Tell me what hydroxides are strong. The soluble hydroxides. And so the strong bases are the soluble hydroxides. All right, what are the soluble hydroxides? List them for me. Group 1. So lithium, sodium, potassium, etc. And ammonium. So ammonium hydroxide, strong base. And so hydroxides are insoluble except for group 1, ammonium, and calcium, strontium, barium. Everything else is weak. So magnesium hydroxide is weak because it's insoluble. You don't get much hydroxide from this. It's an insoluble solid. A little bit will dissolve, but not like sodium hydroxide. Sodium hydroxide lots dissolves. And so the strong bases are soluble hydroxides. Number one. Sodium hydroxide is used in drain cleaner. Magnesium hydroxide is used in milk of magnesia. Milk of magnesia tastes like chalk, it's chalky paste, not very soluble. Is that it? Not quite it. There are more. Give me another strong base. Sulfides are strong bases.
Oxide?
And so we wanted to use the soluble sulfides. So we have the soluble hydroxides, the soluble sulfides. Soluble sulfides are group 1, ammonium, and group 2. So magnesium sulfide would be considered a strong base. How about iron 3 sulfide? Would iron 3 sulfide be considered a strong base? No, that would be considered a weak base. Is that it? What else? Have you looked at your acid-base chart? Tell me some other strong bases. Oxides. The soluble oxides. Soluble oxides weren't on your solubility rules, but they're similar to sulfides, perhaps less soluble. Group 1, ammonium, are pretty much it. Group 1 and ammonium. You expect oxides to be less soluble because of their size. They're smaller in size, so they're going to have stronger bonds. Any others? Amides. Amides are NH2 with a negative charge. It's amides. Amides in general are soluble, so we'll just say amides. And so we have the hydroxides, not all the hydroxides, just the soluble hydroxides. Yeah. And then we have these other bases here. The sulfides, oxides, amides, etc., there are more. These are too strong to exist in water. The strongest base that can exist in water is hydroxide. So hydroxide is strongest base in water. And so we have the leveling effect. It turns out all these strong bases are the same strength in water due to the leveling effect. Strong bases don't ionize. So for example, sulfide is a strong base. What does it ionize to? It doesn't break apart. Strong bases hydrolyze completely. So strong bases hydrolyze. about 100%. And so if I have sulfide, it's going to hydrolyze water. Sulfide is a strong base that attacks water. It's going to form HS minus and OH minus. That happens completely. Oxide hydrolyzes water. This is going to form hydroxide plus hydroxide. Amide hydrolyzes water. To form ammonia and hydroxide. And so the leveling effect is all these are going to level out to hydroxide. And so they have roughly the same strength in water, except oxide has, twice as much hydroxide here. And there are some other smaller, more minor differences, but that's it. Weak bases weakly hydrolyze. Weak bases weakly hydrolyze. That's because they're going uphill. When we look at this, we can use the driving force here. That is, all these are going to be stronger base to weaker base. So we're going from stronger base to weaker base. That's favorable. And that'll be our driving force. However, if we have a weak base like ammonia, ammonia just weakly hydrolyzes. And so if we have ammonia, it doesn't ionize, it hydrolyzes. When it hydrolyzes, it forms a little bit of ammonium and hydroxide. The percentages here I gave earlier at one time. This is greater than 99.9%, and this is less than 0.1%. So just weak hydrolysis here. That's what we have. So getting back to this, I see sulfide there, and there's water present. And so what I'm going to do is we're going to do the inventory for this particular reaction and then see what we have here. All right, so in this particular reaction, I have potassium ions, sulfide ions, sodium ions, chloride ions, and water. I think that was the inventory. Yeah. Potassium ions are pretty much neutral. Sulfide is a strong base, powerful base. Sodium ions are neutral. Chloride ions are so weak that they're considered pretty much basic. Water is going to be both an acid and a base. So we pick the strongest acid present and the strongest base present. Well, the strongest base stands out, sulfide. The strongest acid doesn't really stand out. In fact, we only have one acid, that's going to be water. So if there's going to be a reaction, it's going to be between sulfide and water. Well, we already know that there's going to be a reaction because sulfide is a strong base. Strong base is completely hydrolyzed. And so what we should form here is HS minus plus OH minus. We have a driving force for this. The driving force is going from a stronger base to a weaker base. Here. All right, so we do have a Bronsted acid-base reaction. There's only one other type of reaction that we look for. Do you know what it is? It's redox. Do any of these look familiar from the redox chart? Well, from the redox chart, I have potassium ions. Do potassium ions stand out on the redox chart? And the answer is no, not really. Potassium ions are the second worst oxidizer on the chart, and so they're fairly unreactive. Now where I put my redox chart. Sodium ions are also on the chart. These are extremely weak oxidizers. Potassium ions, sodium ions. Chloride is a very weak reducer. Water is an acid and base. Sulfide is kind of electron rich. You know, oxide we wouldn't really care we wouldn't consider it electron rich, but sulfide's much bigger. You know, it has 2 minus, so an oxidizer can come along and pluck the electrons off more easily than an oxide. An oxide would have a more tighter hold on the electrons. But there's not much in the redox department. Maybe the most reactive chemical here is sulfide, but what's going to oxidize it? Water? No, we'll have a acid-base reaction. Sodium ions? No. Potassium ions? No. Those are just too weak. Yeah. So this is pretty much it for that. All right. Next, we're going to look at iron 3 sulfate and aqueous ammonia. Iron 3 sulfate. Iron is 3 plus, sulfate's 2 minus, so we'll just cross multiply. 2 irons and 3 sulfates. Plus aqueous ammonia. So the first thing I look for is double replacement. But one thing that I notice here is I have ammonia. Ammonia is a weak base. And what do weak bases do? Weak bases weakly hydrolyze water. And so in other words, if I have ammonia here, I can take my ammonia and react that with water to form ammonium and hydroxide. Ammonium and hydroxide. So it doesn't form much. In fact, it's more like this. It's greater than 99.9% ammonia and water and less than 0.1% ammonium hydroxide. But this 0.1% is enough. This hydroxide is very reactive in metathesis reactions. And hydroxide, we'll see, loves to form precipitates. It precipitates all metal cations except for group 1, ammonium and calcium, strontium, barium. And so what we're going to do is we're going to take our ammonia and water. And the ammonia and water are going to hydrolyze weakly to form a little bit of ammonium hydroxide. The ammonium hydroxide, I'm going to put in quotation marks here because it's not stable. But even if a small quantity of hydroxide is generated, it can form a precipitate. And so this gives me my double replacement form. This is AB plus CD. So we're going to take A and D, iron 3 and hydroxide. Plus CB. C is ammonium, B is sulfate. And so sulfate is a 2 minus, ammonium is a 1 plus. So we'll need 2 ammoniums for every sulfate. Yeah. And so aqueous ammonia can participate in metathesis because ammonia is a weak base. Weak base is weakly hydrolyzed. Now, how much hydroxide is generated? A very small amount, but it's enough to precipitate a lot of hydroxide, metal hydroxides, because a lot of these metal hydroxides are quite insoluble. And so this is going to precipitate, and all ammonium salts are soluble, so that's not going to precipitate at all. Okay, let's balance this. I need 2 irons here. 2 irons. So I'm going to multiply this by 2. That gives me my 2 irons. And then I have 3 sulfates over here, so I'll multiply this one by 3. And that's going to give me 2 times 3, 6 hydroxides. And so I need to balance the ammonia and the water, but balancing the ammonium and water gets tricky. So what I'm going to do is I'm going to balance the ammonium hydroxides. So I have 2 times 3 hydroxides gives me 6 hydroxides. So I'll need 6 ammonium hydroxides. And that's going to give me 6 ammoniums, which I have 6 ammoniums over here. So now it's all balanced. But what I need to do is I need to go back and balance the ammonias and water. So if I need 6 ammonium hydroxides, that means I'm going to have 6 ammonias and 6 waters combined. And that will yield 6 ammonium hydroxides here. All right. And so this is going to be the CE as long as I have a driving force, which I do. I have a driving force. The driving force is precipitation. Okay. And we just need a tiny bit of hydroxide to cause this to precipitate. Okay, if I have a double replacement reaction, I'm going to do the CE, the IE, and the NIE. So the CE is this. The IE, do we ionize iron 3 sulfate or leave it together? Ionize it. And so this is going to give me 2 irons and 3 sulfates. It's a soluble salt. Sulfates are soluble. Ammonia. Do I ionize it or leave it? It's a weak base. Leave it. Water. Non-electrolyte. Leave it. Iron 3 hydroxide. It's an insoluble salt, so leave it. Ammonium sulfate. It's a soluble salt, so split it up. 6 ammoniums plus 3 sulfates. Okay. Then we go on to the NIE. The NIE, we just need to cancel out the spectators. And so the NIE here, it looks like sulfate's a spectator. Ammonia is not, because we have ammonia on one side, ammonium on the other. And so the net ionic equation is going to be 2 Fe3 plus 6 ammonias plus 6 waters yields 2 FeOH3 solid plus 6 ammoniums. And that would be it. That would be the net ionic equation for this. All right, so that was number 3. Number 4 and 5 kind of look like a single replacement, but don't use the single replacement method for these unless you know the exceptions. Use the chart method for these. All right, so why don't you go ahead and start these. This is the chart method redox. Normally what I do is if there's no, or do you want me to do 4 and 5? 4? All right, do 4. Chlorine is bubbled in sodium iodide solution, so we'll do 4. Chlorine, what's the formula for chlorine? Cl? Cl minus or Cl2? Cl2. So chlorine is bubbled in, what was it, potassium iodide? No, sodium iodide solution. So this is sodium iodide. Normally chlorine's a gas. We're bubbling it through sodium iodide aqueous. This looks like an A plus BX, but it's not that pattern. This pattern is the X2 plus AY pattern. Are you familiar with the X2 plus AY pattern? If you're not, then you don't have to be. Instead, use the chart method, because then we don't have to remember all these patterns. If we use the chart method, the first step is to inventory. So do we ionize chlorine or just leave it alone? Break apart chlorine or leave it? Break it or leave it alone? Leave it alone. Yeah, we leave it because we only break up the strong acids. Is chlorine a strong acid? No. Is it a strong base? No. Is it a soluble salt? It's not a salt because we need a metal or some cation and an anion. And so we just leave it alone. Sodium iodide, break it apart or leave it? Break it. Soluble salt. All sodium salts are soluble. So we have chlorine, we have sodium ions, and we have iodide. Is there anything else I may be missing? Water. All right, why didn't I try an AB plus CD? Why didn't I do double replacement? I didn't do double replacement because I don't have a compound AB. Well, is chlorine like ammonia? Chlorine hydrolyzes water a little bit to make an AB type compound? No, not really. And so this is not double replacement. Well, if it's not double replacement, I go to acid base. Is chlorine an acid? Is it a base? No. Sodium ions? Iodide ions? No. Only water. So I skip acid base and then I go to redox. And so we're going to use the chart for redox. So if you have your chart handy, chlorine is an oxidizing agent. Sodium ions are an oxidizing agent. Iodide ions are a reducing agent. And water is both an oxidizing agent and a reducing agent. So out of the three oxidizers, which one's the strongest? Chlorine, gas, sodium ions, or water? You may not even need the chart for this. Which one would cause more oxidative damage? If you filled your swimming pool with chlorine, gas, or sodium ions, like sodium chloride, or water? Which one causes more oxidative damage? Chlorine. So chlorine is going to be the strongest oxidizer. Then we have three reducers. Which one is a better reducer? Here we might consult the chart, or have to consult the chart. So is it going to be iodide or is it going to be water? So looking at the chart, we go down. The strongest reducers are down and right. So which one's stronger, iodide or water? I don't even need the chart. I know that iodide is a big or small ion. Iodide is a big ion. If you have a big ion with one electron extra in the valence shell, then the oxidizer can come along and pluck it off easily. So iodide is easy to oxidize. And so it's pretty good. And so what we're going to do is we're going to just copy the equation for chlorine right off the chart. Chlorine plus 2 electrons yields 2 chlorides. But we're not going to copy the equation for iodide right off the chart because iodide is a reactant. So what I have to do is I have to get iodide on the reactant side, the left side. So I'm just going to flip the equation. On the chart, iodide's on the right side. In my reaction, iodide's on the left side. So I'm going to put iodide on the left side. If I do that, then 2 iodides go to iodine, I2 plus 2 electrons. And then we can see here that we have 2 electrons on the left and 2 electrons on the right. The electrons have to cancel. And so that works out. And then we're going to have chlorine plus 2 iodides will yield 2 chlorides plus iodine. All right, then we look for driving force. So chlorine's our oxidizing agent, and its conjugate reducing agent would be chloride. We do this from the half reactions here. Iodide is the reducing agent, and its conjugate oxidizing agent would be iodine. So chlorine is the oxidizing agent. Iodine is the oxidizing agent going backwards. Iodide is the reducing agent going forward. Chloride is the reducing agent going backwards. Then we look which one's stronger, chlorine versus iodine. Are we going uphill or downhill? So if we go chlorine to iodine, chlorine is here, and where's iodine? Iodine's way down here, so we're going from chlorine to iodine. That is uphill or downhill? That's downhill, so we have driving force here. And so the driving force is we're going from stronger oxidizer here, which is chlorine, to weaker oxidizer here, which is iodine. And so this is our driving force. And that must mean that iodide is a stronger reducer than chloride due to the conjugate relationship. And so we have a driving force, we have reaction here. And the reaction is going to be a redox reaction, shown here. All right, let's look at the number 5. Sodium is carefully added to aqueous potassium bromide. So what's the formula for sodium? Na, Na plus, sodium, well, if they don't specify, it's got to be sodium metal, solid sodium, is added to aqueous potassium bromide. Yeah. Potassium bromide is KBr. Hey, this looks like a recognizable pattern. This is the A plus BX pattern. A plus BX yields AX plus B. And so let's go ahead and do that. I recognize this pattern right off. This is going to form sodium bromide plus potassium metal. Then we look for driving force. In redox, we don't look for precipitates. We don't look for stronger acid to weaker acid. And we don't look for gas formation. In redox, we either look at the activity series. And so let's compare sodium and potassium based on the activity series. We have an upside down activity series here. Lithium is most active. And so we're going to compare potassium and sodium. Potassium is more active than sodium, so going from potassium to sodium would be downhill, but going from sodium to potassium would be uphill. What are we doing? We're going from sodium to potassium. This is uphill. In other words, we're going from a less active, lower energy element to a more active, higher energy element. And so the driving for the downhill direction is backwards, like this. And so in other words, we'd go downhill going from potassium to sodium. Going downhill on the right is going up. Okay, so going back to this, we see that there's no reaction. Are we done? It turns out no, this is wrong. There is a reaction. So if there's a reaction, what is it? Well, it's not single replacement. And so a more powerful method, we don't even have to remember single replacement. We don't have to do single replacement. A more powerful method would be the Sharp method. And so I'm going to use the chart method for this. And so what we have is we have sodium metal plus potassium ions plus bromide ions plus there's one more species that's missing. What is it? Water. So sodium metal is actually a pretty good, pretty strong what? Reducer. Potassium ions are really weak, really poor what? Oxidizer. Bromide is an okay or so-so what? Do you find it on the chart? What is it? Reducer. Water is both an oxidizer and reducer. So we got to pick the strongest oxidizer. Potassium ions versus water, which one wins? Looks like potassium ions win. Do you see it? Potassium ions are way up here, water is way down here. Looks like water is the worst oxidizer on the chart. Is that correct? Or is that incorrect? It looks like water is the worst oxidizer on the chart because it's at the bottom on the left side. Is that true or is that false? It's wrong. Water doesn't belong here. Where does water belong? Yeah, here. And that means water is a better oxidizer than potassium ions. And so let's go ahead and do that. The strongest oxidizer will be water. What's the strongest reducer? It's going to be sodium. Sodium is one of the top reducers. It's like number 5, I think. Closest to lithium. And so what we're going to do is we're just going to copy the reactions off the chart. Now sodium, I have sodium on the left side, but on the chart sodium is on the right side. So what I'm going to do is I'm going to flip it so that the sodium goes on the left side. And Na solid is going to yield Na plus an electron. Water is okay. That's already on the left side. So I'm going to go 2 waters plus 2 electrons yields H2 gas plus 2 hydroxides. Okay, when I look at this, I have 2 electrons on the left and 1 electron on the right, so I'm going to double the sodium here. And that means the 2 electrons cancel on the left and the right. And then I'm going to combine these 2 equations. So combining these 2 equations, I'm going to get 2 sodium solids plus H2O liquid. This is going to produce 2 sodium plus H2 gas plus 2 hydroxides. So this is the most probable reaction, but we don't know if it's going to occur. And so what we need, this is 2 waters. What we need to do is we need to look for the driving force. So as far as the driving force, sodium's our reducing agent, and therefore sodium ion will be our conjugate oxidizing agent. And then water is our oxidizing agent, and therefore hydrogen and hydroxide will be our reducing agent. Then we look, are we going to get a reaction here by comparing the strengths? And so you tell me, do we get a reaction or no reaction? there's a reaction. We're going from a stronger oxidizer to a weaker oxidizer. We saw that earlier on the chart, and so that's the driving force. So if the oxidizers are assigned correctly, the reducers are exactly the same, stronger reducer to weaker reducer based on the conjugate relationship. So there is a reaction here. There was no single replacement, but there was a chart. And so the best thing is just to use the chart. It's more general, and you don't have to memorize the exceptions.
Okay.
All right, so why don't you continue working on those reactions at home? And if you have questions, I can help you out with those. I have an office hour tonight as well on WebEx. I'll post the link in Canvas. Okay, thanks. See you tomorrow.
For us.